Hi geographers, welcome to this video about statistical skills. Particularly today we're going to be looking at two things. One of those are averages or measures of central tendency, and the second thing we're going to have a look at are different measures of dispersion. If we start by thinking about measures of central tendency, or what we more commonly refer to as averages, there are essentially three techniques that we can use. These you'll be familiar with from maths lessons in the past. We could look at the mean, which of course is the sum of all of the data divided by the number of observations that we have. This is particularly useful where we have quite a small range within our data. That's because the mean can be very easily affected by outliers or anomalous results. If you have a very large value or a very small value in comparison to the rest of the data set, then it can be skewed quite easily and make the mean less representative. Slightly different alternative to the mean is the median. You may well remember that this is the middle value. When you arrange the data in numerical order, the midpoint represents the median. This is less affected by extreme values and therefore sometimes is a more useful measure, and very often it's worth calculating both the mean and the median when you're looking at a set of data. Less frequently used, but another option that we've got to us is the mode, and this is the value that occurs most frequently. In a geography context, this is probably most important when the data has been put into categories, and you can see perhaps which category has been selected most often, perhaps in the responses to a questionnaire, for example. In terms of calculating the mean, median and mode, we're going to have a go here with some data that we've got for a river in the north of England, and we've got the discharge of that river for 4 months of the year, January, April, July and October, and we've got it for 19 years going from 1994 up to 2012. In the first case, if we wanted to calculate the mean of the data for January, we would need to firstly get our calculator out and find the sum of all of those numbers there. So we could do 56.68 plus 70.96 plus 86.42. We could go down and add all those numbers up, and that would give us a value of 1119.03, and we would divide that by the number of observations that we've got, in this case the number of years, which is 19. So in this case, our mean would be 58.90. We could work that out using a calculator. The median is a little bit more complicated to calculate. For this, we would need to get the data in numerical order, ordered from highest to lowest. So what I'm going to do now, I'm going to work my way through the data from this column, and I'm going to be writing it down here in numerical order from highest to lowest. So my highest value, which I've got in this column, is 99.70, the value for 2012. So I could put that here. I could then carry on down and look for my next highest value, okay, which is 93.93 here. Sometimes it's a good idea to cross these off as you go. 93.93, and so on. I could work my way down that list. So there I have all of my data in numerical order. Next step would obviously to be finding the middle point of those bits of data. There's two ways we can do that. If you've got quite a large number of data sets, you can think about using a little equation, okay, which is n plus 1 divided by 2. Okay, so the number of data sets in this case would be 19. I could add 1 to that, which would give me 20, and I could divide that by 2, which would give me 10. Now 10 is not my median, but it's the 10th point within my set of data. Okay, that's one way of doing it, and I could start at the top and I could count down 10 bits of data. Sometimes if you've got a small number of sets of data, you can simply count from either end until you find the middle point. So in this case, my 10th point is going to be here, okay, 69.94. So in this case, the median is 69.94 QMEX. Okay, you must remember that we give our data in the same unit of measurements that it's been collected in. Okay, and that says here that that data has been measured in QMEX. So that's how we go about finding the mean and the median. What I'd like you to do is see if you can have a go now and calculate both the mean and the median for the data for April. So I want you to work out for me the mean and the median for April. Okay, so in terms of the mean value, hopefully you managed to calculate the total being 462.97, and you divided that by 19 being the number of observations, which gives you a mean of 24.37. Okay, and the median value, if you manage to put those numbers in the correct numerical order from highest to lowest and then found your midpoint, you would have found 24.68 as being the median value. We can see these are quite similar. So 24.68, 24.37, they're very close together. So what that suggests is that there's not that much variation within that set of data. If there was a significantly higher or lower value in 1 year than the other 18 years, then that would skew that bit of data. If we remember back to the last slide, for January, the mean was 58.9 or 58.90, and the median was 69.94. Okay, so a much bigger difference there. And the reason the mean is lower is because it's been dragged down by that unusually low value in 2010 there. So that score of 10 is very much an outlier or an anomalous result compared to the other years. So that has brought the mean down in comparison to the median. So the second thing we're going to consider in this video are measures of dispersion. And these are ways in which we can look at how spread out a set of data is. And for certain bits of data, that's really useful to know. We want to know how variable a set of data might be. And we can use three different methods to calculate the spread of data. Each of these techniques that we're going to have a look at gets slightly more complicated, but it does get slightly more reliable as we go through. So the simplest and most straightforward one, which you'll be familiar with already, is the concept of the range. Okay, and this is the highest value minus the lowest value, and it's a very crude measurement of how spread out the data is. And the reason it's quite crude is because it can be very easily affected by extreme or anomalous values. A little bit like the mean can be skewed by a particularly high or low number, the same can go for the range. So if, for example, you had 10 houses on a street and 9 of those houses were worth £100,000 and one of those houses happened to be worth £1 million, then the range of house prices is obviously 900,000, even though 9 of the house prices are exactly the same. So the range can be skewed by those extremely high or low values. A slightly more reliable measurement is what we call the interquartile range, and this measures the dispersion around the median. So we look at where our data lies in relation to the middle point, and it calculates where the middle 50% of the data lies. So it gives us a range within which 50% of our data lies, and because it's dealing with 50% of the data rather than just 2 values, it's slightly more accurate than the range. Even better still is a measurement that we call standard deviation, and this measures the dispersion around the mean. So we need to calculate the mean value, and then we look at, on average, how much each point differs from the mean. And because it's taking into account every single value rather than just the middle 50%, it's therefore even more accurate than the interquartile range. So I'm not going to talk to you about how to calculate the range because that's a very, very straightforward calculation that you'll already be familiar with. But we are now going to have a look at the interquartile range and standard deviation. So a little bit more detail about the interquartile range. As I've said already, it's a measurement of where the middle 50% of our data set lies. What we have to do is to imagine that our data is spread out from highest to lowest. We find where the median is, where the middle point is, and then we look where half of the data is around that middle point. So you can imagine that we split our data into 4 chunks. Okay, we refer to each of those chunks as quartiles, often represented by this letter Q. So the bottom 25%, that's our first quartile. The next 25% is our second quartile. Our third 25% is our third quartile, and our top 25% is our top quartile. Okay, so we're dividing them into 4 groups, and we are trying to find this middle bit here. What is the difference between the lower quartile and the upper quartile? Where is the boundary between the bottom 25% and the top 25%? And if we can find where those boundaries are, we know our middle 50% lies in between the two. There are a couple of different ways that we can calculate the interquartile range. One of them just simply involves us counting in from either end of our set of data, and one of them involves the little equations that we've got on the right hand side. I'll talk you through both of those and I'll show you an example in just a second. But this is a little checklist that perhaps you can refer to in future. So we want to arrange the data in numerical order. Generally, we would always go from highest to lowest there as well. That's a good thing to remember. So we would order our data from highest to lowest in numerical order. We then want to find the median value. Sometimes you'll see this is referred to as Q2. We would then find the position of the lower quartile, which is halfway between the median and your lowest value. We then find the upper quartile, which is halfway between the median and our highest value. And then we simply find what the difference is between the middle, and then we simply find what the difference is between the upper and lower quartiles. We calculate that difference just like we do for the range, and we will be able to get an answer to tell us where 50% of our data lies. Now, there are some calculations that we can use to help us find the median upper quartile and lower quartile, and this is particularly useful where we've got large numbers of sets of, and this is particularly useful where we've got quite a large set of data. Rather than having to count inwards from both ends for 100 observations, for example, we could use this calculation to help us find where the median and upper quartile and lower quartiles are. N, in this case, as with all statistics that we're going to have a look at, represents the number of values in a particular set of data. So we're going to have a look at an example together here, and for this example set of data I want you to imagine that I've gone along and I've collected the ages of residents in one street. So I have asked 9 people along a street how old they are, and I want to see what the range of data is here by examining the interquartile range. First thing we need to do is we need to find the median value, and this can be done in one of 2 ways. We can either, with a relatively small set of data like this, we could just count from either end until we find the middle. So I've got 1 at either end there, 2, 3, 4, and then I land on this one here being the middle value. So in this case, the median value is 72. However, if we had quite a large number of data sets, let's say we had 100 people, then that would take quite a long time to count inwards from either end, and we'd be more likely to make a mistake and get it wrong. So we can use this little equation here to help us calculate which position we've got to have a look at. So in this case, n refers to the number of values, which is 9. So we're looking at 9 plus 1 divided by 2. Well, 9 plus 1 is 10. Divide that by 2, we get 5, okay, which marks the 5th value that we have to look at. So in this case, 1, 2, 3, 4, 5. So it takes us to the same point, no matter which way we do that, we can find the median, which is our middle point. So in this case, Q2, or our median value, that is 72. We then want to go about finding where the upper and lower quartiles are. Again, we could do this by counting, and it's worth remembering if you do that, then you ignore the median value and you would count inwards from either end. Okay, and at this point, you see, we don't actually land on a value. We would land somewhere in between the two. Okay. Again, we could use this calculation to work this out. So we could do n plus 1, which is 9 plus 1, divided by 4. So in this case, the answer is 2.5, or the 2.5th value. So again, 1, 2.5, halfway between the second and third value. So in this case, our Q3, our upper quartile, lies somewhere in between 81 and 77, in fact halfway between the two. So we could actually work out what the halfway point is. We could do 77 plus 81 and divide that by 2 to give us 79. So halfway between 81 and 77 is 79. So that is our upper quartile. We could do the same for the lower quartile. In this case, 3 times 9 plus 1 divided by 4. Okay, so 9 plus 1 is 10. We times that by 3, that gives us 30. We divide that by 4, that gives us the 7.5th value. So again, 5, 6, 7, 8. It's going to be halfway between 65 and 64. Well, those numbers are a little bit closer together, so it's easier to maybe work that out in our heads. 64.5. So our lower quartile is 64.5. To calculate the interquartile range, all we're doing is looking for the difference between 79 and 64.5. We're looking for how separated those two numbers are. So we could do 79 minus 64.5 would give us 14.5. So the interquartile range for this set of data would be 14.5. Now on its own, that doesn't really mean anything other than, I guess, the lower the number, the less spread out the data is, the higher the number, the more spread out it is. But it's very useful if we had two sets of data. Perhaps I looked at 2 streets and I wanted to compare those 2 streets in terms of the ages of people, then using the interquartile range would give me a good indication of how spread out those sets of data were and whether one was more widely distributed than another. Okay, over to you this time. What I would like you to do, going back to our data that we used earlier for January, the river discharge of this river in 19 different years from 1994 up to 2012, I'd like you to go about calculating the interquartile range. Remember that you need to firstly order the values from highest to lowest, and then you could use these calculations here to help you work out where those points are, and then from there calculate the interquartile range. So pause the video and on your worksheet have a go at that, please. Okay, so we're going to check our answers to this now. Hopefully you use these calculations to help you find where the median was. So in this case, 19 was the number of observations plus 1 divided by 2 gives us the 10th value for our median, which would be here, 69.94. So this is Q2, our median. The upper quartile would be 19 plus 1 divided by 4, which is going to give us the 5th value, which would be up here, 81.19. So that's Q1. And the lower quartile would be 3 times 19 plus 1, or 3 times 20 divided by 4, which is going to give us the 15th value, which would be down here, 31.9. 81.64. So our interquartile range is the difference between those two numbers, which is 81.19 minus 31.64, which gives us an interquartile range of 49.55. And remember, we need to use the units of measurement, which were in QMAX. Okay, well done if you managed to get that right. Again, on its own, that number doesn't mean a huge amount, although again, we can appreciate the fact that the higher the number, the more variable the data is. And if we had worked it out for more than 1 year, we would be able to make some comparisons between those years in terms of their variability in river discharge. The final technique that we're going to have a look at is a statistical technique known as standard deviation. So again, this is more accurate than the interquartile range because it's taking into account every single piece of data within the calculation. So it is a little bit more long-winded to do, but it's worth it because we can be much more confident in the value that we get out of our calculation. Essentially, the standard deviation is telling us the average difference from the mean. So on average, how much does our set of data vary around the mean? And again, we can compare sets of data using the standard deviation to tell us how spread out they are in comparison to one another. One thing to say about standard deviation before we start looking at how we do it is that it assumes that our data has what we call a normal distribution, which is what we can see outlined here. And most things, if we collect enough bits of data, tend to produce this sort of distribution. So let's imagine we measured the height of everybody in the school. We would find that there would be a small number of very tall people and a small number of very short people, and most people would be somewhere in the middle. Okay, and standard deviation assumes that this normal distribution exists, and therefore we can assume that 68% of our data lies within one standard deviation of the mean, either one standard deviation above or below the mean, and 95% of our data lies within two standard deviations of the mean, either 2 above or 2 below. Now, this will make a bit more sense when we come back to it later with some actual data attached to these figures at the bottom, but it's worth just pointing out at this stage that this is the principle on which standard deviation works. So this list of instructions here might look quite complicated, and I've really just put it on the screen so that you can have this to come back to. A couple of things to point out to start with. Standard deviation relies on calculating the mean, and the mean is very often represented by this symbol here, x, with a little line across it known as x bar. Okay, we will be looking to subtract the mean from each of our data points, squaring that number, and then adding them up to basically give us this part of the equation. So this rather scary looking part of the equation here, we can actually work that out using a data table that I'm going to put on the screen in a minute. We then divide that total by n, which is the number of observations like we did before. We square root that number and that will give us our standard deviation, and that's what this symbol here represents. Okay, so you've got this list of calculations to come back to if you need it, but we're going to work through an example together and then you're going to do one on your own. So back to our data for those rivers, and we're going to look at just the month of January, and we're going to calculate the standard deviation for January. The first thing we need to do before we can start to fill this table in is we need to work out what the mean is. Remember, mean is represented by that symbol x bar. We did work this out earlier. We had to add up all the values and divide it by 19, and that gave us 58.90. Okay, so what we're attempting to do now is do this. So what we want to do now is fill in this first column, which is represented by x minus x bar. Okay, in this case, x being the value in this column minus the mean. So to work out the value for this box here, we would do 56.68 minus 58.90, which would give us minus 2.22. Okay. The same for this next one here. We would do 70.96, subtract 58.90, and that would give us 12.66. Okay. What's quite a good idea to do is actually, when you've calculated these on your calculator, as soon as you've got the value, is to hit the squared button, because that will then give you the next answer for this column as well, rather than working out this whole column and then having to go back and type all those numbers in and square them. If you hit the squared button after you've calculated this number, we can work out what x minus x bar squared is. The main reason we are squaring this number is to help us get rid of the negative values. So when you square a negative number, the negative sign disappears. That becomes a positive number. We'll get rid of the squaring later on by square rooting the value. So minus 2.22 squared, if we type that into our calculator, we would have 4.93. Same for 12.66 squared, we would get 145.44. What we can do then is go down the rest of this list and we can work out what those values would be. Okay, so 86.42 minus the mean would give us 27.52, and we would square that number and we'd get 757.35. I'm just going to whiz down now and put all of these calculations in. Okay, so just to recap, what we've been doing there then is working out the difference between our value for the month of January and the mean. We've then been squaring that number to give us the value for the final column. The last thing we need to do is to add up that final column to give us this value here. This symbol is known as sigma, Greek symbol, which means the sum of. So in this case, we're looking to sum all of that column x minus x bar squared. So we can add all of those numbers up and we get a value of 14,450.57. We're always going to give the data to the same number of decimal places as it was collected in. So in this case, 2 decimal places. When we've worked out the differences, we've given that to 2 decimal places. When we've squared it, we've given that to 2 decimal places as well. Okay, and when we've added it up again, we'll give that to 2 decimal places. What we can now do is start substituting some numbers into our equation so that we can work out what the standard deviation is for this set of data. So we know what the sum of x minus x bar squared is. We just added it up down here. It's 14,450.57. So we can do that divided by n, which in this case is 19. We have 19 years in our table, and we can square root that whole number. If we were to work that out, that is the same as doing the square root of 760.57. If we calculated what this bit is and then square root 760.57, we get 27.58. And again, we're going to give that in the same units of measurement as we used before, which was QMEX. And once again, this number on its own doesn't mean a huge amount. Obviously, the larger it is, the more spread out the data is. The smaller it is, the less spread out the data is. We could certainly use this to compare more than one month or more than one river looking at the same set of data. So going back to our diagram earlier of this normal distribution, we can actually put some numbers in here to help us understand how the standard deviation relates to the distribution of our data. So our mean was 58.90. So we can imagine this midpoint here in a normal distribution. This represents the mean, 58.9 QMex. Now, 68% of the time, the river's discharge is going to be within one standard deviation of the mean. So we could be fairly confident that 68% of the time, the discharge of that river is between 31.3 QMex and 86.4 QMex. Now I've worked these numbers out by adding or subtracting our standard deviation from the mean. So 58.9 plus 27.58 gives us 86.48. 58.9 minus 27.58 gives us 31.31. So we could be fairly confident that 68% of the time the river's discharge is between 31 and 86 QMex. We could even go a step further and we could subtract another standard deviation or add another standard deviation on at the other end. So 86.48 plus 27.58 would give us 114.06. And if we were to subtract another standard deviation off the end here, we would get 3.73. So again, we can say that 95% of the time we would expect the river's discharge to be between 3.73 QMex and 114 QMex. So that's how this normal distribution relates to the standard deviation. So over to you then. I've got an example here that I'd like you to have a go at, and a student has collected some data investigating the differences in the levels of affluence between two parts of a city in the UK. They've gone to each part of the city and they've done a questionnaire and they've collected some data about the average weekly income of residents in two parts of a city. Area A has already been done for you, and the standard deviation of Area A is £101.43. So on average, salaries vary by £101.43 within Area A. You've got the data on your worksheet and on the screen here for Area B. What you need to do, work through the standard deviation calculation and then come to the decision about which area, Area A or B, has the greater variation based on the result that you get in this test. Okay, so to go through the answers then, on the screen here I've put up the calculations that you should have done. Notice that I've just rounded those numbers to 2 decimal places based on the idea that it's measured in pounds, so generally we'd think about pounds and pence, wouldn't we? So 2 decimal places is fine here. Don't worry if you've written more than that, that's absolutely fine. Hopefully you've got an answer that's very close to this anyway. First thing you should probably do is check your overall total down here for the sum of x minus x bar squared. If you got that right, if you got 433,052.63, then your calculations will have been done correctly. If you got a different answer, then you've gone wrong somewhere. It's worth just going back and then working through and seeing where you went wrong. You then needed to obviously substitute that value for x minus x bar squared into the equation. So you should have been doing 433,052.63 divided by 19 and then square rooting that answer, which would have given you 150.97 or £150.97. So we can see that this standard deviation for Area B is higher than the standard deviation for Area A. What that means is that the income in Area B is more variable because it has a higher standard deviation. So that is the conclusion or summary that you should have come to based on those 2 bits of data. Well done if you managed to get all of those points correctly.